I'm going to talk about one experiment mainly, treasure hunt, and then sort of two experiments which we are currently doing, which were both inspired by this experiment. Okay. So the motivation was basically that we wanted to test social learning in the field. There's lots of evidence that social learning is important. There is actually one of the studies, one of the earliest studies on that is from the 1940s, by Lazarsfeld in the social sciences, who showed that he looked at the Truman election in 1948, and he checked how, who influenced whom, who were the biggest influencers, newspapers or friends, when it came to making a, submitting a vote. And he argued that from his interviews that friends were more influential than mass media for influencing your voting decision. Okay, and there's a lot of recent work on technology adoption by Esther Duflo and others, and Colleen Udry on pineapple farming, who looked at how farmers in the developing world how they make decisions. And given that they don't read as many trade magazines, etc., as farmers in the U.S. say, in the developed world, they depend on learning from their friends and peers, and so this has been sort of a rich area of research and development economics. Okay, and then I guess there's a lot of expectation if you look at, for example, the recent Facebook. Facebook IPO, there are great expectations people put into things like Facebook to use it for marketing new products, to use a social network as a way to sort of disseminate information about the network, about new products, and that the social marketing might be more successful than standard marketing in reaching customers. Okay, so what we're trying to do is we're trying to sort of do a field experiment and do it with real subjects and see how people learn. And we want to sort of, in the first paper I'm talking about, we just want to distinguish between different theories of social learning and how people aggregate information. Okay, and in the second experiment we use, we build on this and we use that as a way. Well, I explain what we do in the second one when I come to it. So, okay, so just to sort of a recap, most of you will be familiar with that, just in terms of theories of social learning, non-Bayesian theories of social learning. There's a Bayesian approach that if you assume people are fully Bayesian, you can do theory on that, and Sanjeev did work on that, for example, and we focus here on theories which are not fully Bayesian. And sort of one is, the most popular model is the growth model. So where agents average just by, they learn by averaging the opinions of their neighbors. And the other one is, we call the streams model, where they tag the information that's transmitted through the network is tagged by the source. So who is transmitting this information. And there's a recent paper which exploits that. For example, it's Bimbikis, Semuglu Bimbikis Ozdak Lars from MIT. And I just want to sort of tell you some of the differences that exist between those two learning, between those two learning models. So think about the following framework here. There's a sender, there's a receiver, and there are two intermediaries. And so the receiver gets information from the sender, and the information travels to these two intermediaries. Okay? In the de Groot model, say both intermediaries transmit the information, the receiver will treat these sort of two pieces of information as independent. In a streams model where this information is tagged, the receiver will realize that this information is coming from the same sender and will count it as one signal. Okay? So this has some obvious implications. One of them is that if we are in a de Groot world, we might have a harder time, for example, distinguishing between truth and sort of urban myth. But an urban myth is something which started maybe with a small number of people. One guy is, for example, saying that I don't know if you heard about this, but this is an urban myth that, apparently, like, there's this urban myth in the US that you can tip cows if you approach them at night when they sleep and you tip them, they fall over, okay? And it's an urban myth, it's not true. These are far too heavy animals. You cannot tip them over, even when they sleep. But
your experience in Iowa.
well, I have never tried it myself, but I was actually heard that before, and sort of, we had a little poll at MSR New England, and like amongst 5 people actually, 3 people heard of it, and they thought this was a fact. I mean, which might say something about the kind of people who are at MSR New England, but anyway, so. So basically the idea is like, if like the sender is telling the signal, you can tip these cows in Iowa, and there's only one sender, and maybe he saw somebody tip a cow, and this was just a sick cow, and he interpreted it this way, and he sort of told this information, and it spreads. Then basically the growth world, it can spread, but it will sort of go through different paths, and in the end you might reach, for example, this through 2 paths. You might interpret this as 2 independent signals. Or it goes through more paths as 3 or 4 independent signals. And you might think, well, there must be some truth in that. Several people told me that you can do this incredible thing. Whereas if this information is tagged, I might realize, well, this all comes down to this single crazy guy who saw this or thought he saw it, and it's actually not true. Now, journalists have this rule that serious papers tend to have this rule that if you have a big sort of piece of info, big news, you have to identify it through several independent sources. You don't want to rely just on a single source. And they have it differs by newspaper sort of what means to have an independent source, but basically, you want to sort of make sure that this information doesn't originate from one origin. Yep.
But here you are assuming that information is coarse enough that you are not communicating with the sender.
Well, in a streams model, you do communicate what, you actually, in a streams model, we call it streams because you communicate the full set of signals. I tell, I might tell you that Sanjeev told me that, and, my wife told me that, and, my brother told me this piece of information, and you get everything I know, the full set of signals, okay? In the growth model, all I'm telling you is that 3 people told me that, okay? And you just aggregate that up by sort of, 3 people told you that, and somebody else tells you 2 people told you that, so you think these are 5 signals. Okay? Give you another example, for example, say you're deciding between graduate schools, and you ask people should I go to MIT or Chicago? If you have 2 people say from NYU tell you should go to MIT, maybe that's less informative than 1 person from NYU saying 1 person from Stanford, because MIT, NYU people might have a bias towards MIT. NYU people might have a bias towards MIT, but if you have 2 totally distinct parts of the social network, it might be less likely that they have this bias. Okay, so these sources are more independent. Okay, so this is sort of one reason why it might matter, how we aggregate information, if it's tagged or if it's untagged. Another thing is this echo chamber effect, like Sansin and so on talks about, where we live in an island of people. There's homophily, so we live with people who are similar to us, and it's more likely that we are connected because of clustering. It's more likely that we have common friends within an island than across islands. Okay. If this is the case, then it tends to be also the case that if information is originating from within the island, because it reaches us through several paths, we might overweight it compared to information that comes from outside. Okay, so there might be echo chamber effects which might be amplified by this kind of learning. Okay, so let me tell you what we did in this treasure hunt experiment. So this was done at Harvard. This was done with sophomores, juniors. Well, actually, so we did a series of experiments a year before we ran this experiment. And at that, yeah.
You have to explain, most English people won't know what a sophomore is.
Oh, okay, right. So sophomores are second year.
Out of 4 years.
out of 4 years as second-year students. Out of 4 years, juniors are third years and seniors are fourth-year students. Okay. And so this is an experiment. Like you can tell, like there are about 1,600 students in 1 year at Harvard. And this, we ran this experiment. This was a series of experiments we ran, which resulted in a different set of papers, which we ran together with Facebook. So they put a link on the Harvard Facebook page, and they invited them to play a trivia game. And and the trivia game was basically designed to sort of find out who their 10 best friends were. Because on Facebook, people tend to have like 100, 200 friends. You don't know who their best friends are. So some people have used various mechanisms to find out who the best friends are, who tags you in pictures, whom you send direct messages to, etc. So we used a trivia game to do that. And the way it worked was, amongst your Facebook friends, you could select, 10 people to play this trivia game with. For example, I might select, Adam. And they couldn't be your room. Yeah. So, no, they could. Yeah. So you selected these 10 friends, and then what we did was after you selected them, every night a computer would choose amongst these links that were selected. And then, for example, if I selected Adam and Adam also participated in the game, the computer would contact Adam, would send him an email saying, there's a message waiting for you, click that link. And that link, he would click that link, and I would ask them, like, what time do you get up in the morning? And he had, five choices there. Or what kind of shoes what's the color of the shoes you wear? Would have various choices. He would answer these questions, and then immediately after he answered the question, I would get a message saying that, there's a question waiting for me. I click on that link again. When I click on the link, it asks me sort of, what time does Adam get up in the morning? I have 10 seconds to answer, otherwise the question disappears. So I don't have enough time to contact Adam, okay? And so that worked actually pretty well. So for a subset of people, we did a separate network survey, and we got about 2/3, we did the separate network survey a couple of months before, and out of 10 people on average, 6.5 coincided with the people we got from this trivia game. Okay, so we had this social network data, but we ran actually this treasure hunt game a year afterwards. So the seniors were gone, so the only people who were left the sophomores and juniors, who the following year they were the juniors and seniors. Okay, so we had some aged social network data. And okay, now for the treasure hunt, we invited them with an email to this experiment. So everybody who participated in the experiment the year before was invited, and they had to solve an imaginary treasure hunt. And so this was a treasure hunt. There were 3 questions, and there were binary answers to that. So there's treasure was discovered at the bottom of the ocean or on top of Mount Everest. So you could choose one of the 2. It was found by Julius Caesar, Napoleon Bonaparte, and treasure is buried in Larry Summers' office under the John Harvard statue. So there were like 2 choices, 8 combinations, okay? And everybody got initially one signal, which meant, he got one suggested answer. And they were told that basically the majority of people would get the correct answer, but your particular signal might not be correct. Okay? So essentially, if you ask everybody at Harvard who played the same game and then just do majority voting, you would do the correct thing. Okay? But your particular signal might not be quite correct. And so we didn't want to make it too easy, so the way we did this, 58% of people got the correct signal, 42% got the incorrect one. A little bit fuzzy why we chose exactly those numbers, but those are numbers we chose. Okay, the experiment lasted 4 days, and it had a stochastic end date. And they could log into the site as often as they wanted. Okay, and so we did the stochastic end date because we basically wanted them to update as the experiment went on. We wanted them to update their guesses. And so this was an easy way of doing it by having a stochastic ending. Because if we would have said it all ends like on Sunday at 12 p.m., they might just wait until an hour before and then submit their guesses. But what we wanted is we wanted to submit their guesses often. And so, on average, people, I think, submitted 2.5 or 3 guesses. Okay?
So where did the signal come from?
We provided the signal.
But, so you said 48% was incorrect?
58 was correct. 58% was correct. 42% was incorrect.
And by incorrect, you mean at least one of the questions?
Each of those independently was incorrect. So for example, the treasure was discovered, if the true answer is on the top of Mount Everest, 58% would see that on top of Mount Everest. But 42% would see the other thing. And all we told them is the majority of people get the correct one. We're not going to tell you exactly. We're not going to tell you, obviously, what's the correct one. You have to find that out yourself.
So the fraction of people who got all the 3 things correct
Mm-hmm.
is actually quite small.
Yes. 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 Yeah. That's right. Okay? All right. And, they could submit their guesses. After they submit a guess, they got an email saying, thank you for submitting the guess. If you want to log in back again, just follow this link. Okay? And, I left out something, which is we captured also the kind of people they talked to. We captured the actual conversation they had, but I'm going to show that to you on a later screen. Yeah?
You investigate framing effects by just, because many people would think, oh, treasure, bottom of the ocean, and probably by Napoleon.
Yeah, so
not there.
no, we didn't. We didn't actually. Yeah, no, we didn't. I mean, to some extent, we didn't see, what I can tell you is we didn't see a big, if you put in a sort of question fixed effect to sort of see if there are differences, between those questions, we didn't see a big effect there. We didn't see anything that sort of stood out.
So what was the right answer? What was the right answer?
Honestly, I don't remember. I don't remember what was the right answer. I wrote that down, and I meant to put that in the slides for a long time, but I haven't. Okay, so let me tell you, how we analyzed this. So the simple thing we did is we just ran a logic regression. So let me tell you what we put on the right-hand side. The second equal sign should actually be a plus sign. So there's guess, and then, so the guess is, so we coded the data the following way. If they got the correct answer on this question, we coded as a 1 on the left-hand side. Otherwise, we coded as a 0. Okay? So it was 0, 1, so it was binary, so we could run a logit type regression. And on the right-hand side, we put in a fixed effect alpha, a constant alpha. So what does alpha capture? Alpha captures everything which is not, captures any external information they have. For example, if they conduct a house poll where they kind of are, or they conduct a poll at the dinner table, because these people live in houses and dorms, so maybe they conduct a poll at the dorm. Everybody raise their hand who thinks it's A. They're quite likely to get the correct answer right this way. And and then independent of what the signals of their friends are, they would, because of this effect, they would get it right. So this is captured in the alpha. So this is absent of their friends' information, their probability of getting it right. Okay? Then, of course, they have their own signal. And then they have the signals of friends and the signals of indirect friends. And the way we code that is the following way. Their own signal we code as 1 if they have the correct signal, and as -1 if they have the incorrect signal. And for the indirect friends and the direct friends, we do the same thing. So we take, we code the signal as a 1 if a particular friend got the right signal, -1 if they got the wrong signal. And we just sum up over all these friends. Okay? So for example, yeah.
You only told them that the majority of the students got the right signal.
Mm-hmm.
Why did you not tell them exactly the percentage?
Actually, ex post, this is something we should have done. I agree with you. It would have been easier, you know, it's not on the slides, but it's in the paper. It would have been easier to say it's 58%. Yeah, would have been cleaner. So we just wanted to sort of, you know, because it was a web-based experiment, and we wanted to sort of keep it as simple as possible and reduce the numbers as much as possible. But I think that particular information, even if it wouldn't have mattered, it would have made it a little bit cleaner, you know, for somebody. Yeah.
So the sum of signals, there are 3 signals.
Yeah, but this is independent for each question.
Oh, I see.
Okay. Yeah. So for example, if you and Peter are my friends, you both had the correct answer, I would code that as 2. 1 plus 1, right? If both of you have the incorrect answer, I would code that as -1, so it's -2. Okay? And we did this +1, -1 coding because we kind of assumed that, you know, we exactly assumed that there is no, so the analysis kind of assumed that the answers are really symmetric. And so, you know, I'm influenced in either direction just as much, you know, if you know, you have the correct answer or the incorrect answer. Yeah.
Here you're considering just the final answer? Because you
Yes.
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 Including all the...
Yeah, we focus here on the final answers. So we're working on this, doing this with the intermediate as well, but it's sort of more tricky. So here, what I'm going to show you is the final answers they give.
Why don't you include like the time to respond to answer? So the time that I take to answer, because...
So we're going to include that because here, I'm just using the social network data we collected the year before, okay? But in a couple of slides on, we're actually going to use conversation data because we asked them each time, whom did you talk to since the last time? And we're going to use that as well, and there we're exactly going to use the timing, because, for example, it might be that I report that I talked to Peter, and Peter reported before that he talked to Sanjeev, okay? So in this case, I know that I could have learned from Peter his signal, and also Sanjeev's signal indirectly, okay? So we do that, but not on this analysis here. Yeah.
So there's something I'm not clear, I understand. The signals are coded as +1 or -1.
Mhm.
Whether they're correct, but when you're guessing, you don't know the correct answer. So I'm kind of not sure how.
Yes, so what we did is, that's right. So what we did is we just recode all the data, okay? And we just see if their answer is correct or incorrect. And we also code if their signal is correct or incorrect, okay? It's just a way of coding their signals so that we can run this type of regression.
But at the time of guessing, the person doesn't know the correctness or incorrectness.
No, that's right. That's right. But I mean, in this case here, like, you know, with this empirical model, essentially what this just means is, like, if you forget about the fixed effect, about the alpha, like if I invert all the signals and I invert all the action, it's exactly the same thing. So it just means, like, you know, the probability that you get the answer correct is exactly the same as the probability that you can't get the answer incorrect if I switch everybody's signal, including your own, okay? The only thing in that logic which doesn't quite fit is the alpha, which is a fixed effect, because that sort of captures what comes from outside your immediate friends, okay? And that probably is, you know, things like house polls, you know, the house mailing lists. We monitor the house mailing list just to see, like, you know, how many people do this kind of thing, that they have this chain email. In one house, they did that. You know, fortunately not in the other houses.
So I guess the second equal is time included.
Yeah, that's wrong. It's my fault, sorry. Okay, good. So this is this regression. This is okay, and we do a logic regression. So we have an error term in there. So we assume that, you know, people essentially use majority voting, and you know, there's an error term because, you know, depending on what the signals are, they might still submit a different answer. There's some noise there.
Can you separate the error term from alpha? Because if you added a constant.
Right. Well, it's a logic regression, right? There's a constant there, and then there's the epsilon. So I guess it's in the functional form of the logic regression, right? The way it's estimated. Yeah. So okay, so this is the, this is the estimation result using the social network data. And just to sort of explain to you what this means, D1 means these are the sum of signals of direct friends. And 0 means, so the first number is whether they are direct friends or indirect friends. 2 means indirect friends. And we ignored higher order friends. So we ignored friends at distance 3 because we saw that it actually didn't change the results. And the second number means how many extra paths connect you. Okay? So for example, D10 means this is a direct friend and there's no other extra path connecting me to this guy. Indirect path of length 2. Whereas D13 means this is a direct friend. Say Peter is a direct friend, but they're also like, we have 3 common friends. Okay? And these 3 common friends have 3 paths which connect me to Peter additionally. Okay? All right? And the reason why we break this up is because you can see, like, if you have a tagged or an untagged model, it matters. Because if you have not tagging, these things should be additive, right? The more channels there are, the more sort of I overweight the information I receive from Peter.
And is this the individual element, not like the total? Is this the final answer or each of the individual?
Well, this is just, yeah, so this is just basically, this is the bin of people who are direct friends of me.
And is it on the final, whether all 3 elements of the answer or just one?
It's just for one question.
One question.
Uh-huh. Yeah. And for some of the regressions we pool it and then we have clustered errors on the individual level. And D20 means, so this is exactly the same. D20 to D23 is, these are people, this is a friend, this is an indirect friend, a friend of a friend, whom I connected to only through a single path. Okay? And then D21 is like, somebody I'm connected through to 2 paths essentially. And so on. Okay.
So sorry, what did we correct? I'm sorry.
Oh, sorry, I forgot this. So I got carried away. So yeah, so basically what the thing here is like, I argue that we don't learn as much from this as we learn from stuff later, but basically, you see here that the, so basically there is, the own signal, this is correct signal, the own signal matters a lot, okay? But the signals of friends, doesn't matter as much. I mean, the coefficient is 10 times as small, okay? But it also doesn't change for the direct friends, it doesn't change, like, if I have more connections to them, okay? Whereas for the indirect friends, the sort of effect is almost like linear. Like, here it's small, then here it's doubled, here it's about 3 times as big. Okay?
So that says that if I have more paths.
If I have more paths to indirect friends, I weigh the information more. If I have more paths to direct friends, it doesn't seem to imply that I weigh the information more. So I'm saying that, it's a little bit hard to interpret that because
Do I know that? I don't know how many paths I've got to interact with.
I don't know. I mean, there's actually, there are these papers which look at sort of what you know about networks. How much network knowledge is out there, right? And I think Sanjeev has a paper on this too, right? And so the people are pretty aware of what their direct network is, but even at distance 2, sort of it gets fuzzy. I don't know all your friends, even if I know you quite well. Right. But this is not, but this is not as important here because it doesn't really matter if they know their friends or not. I mean, the degrowth model is quite mechanical in the sense that, they just aggregate it up. Yeah?
Isn't interpreting the coefficients here a little difficult because your own signal is binary 0, 1.
Uh-huh.
But the other
No, your own signal is also -1, 1.
-1, 1?
Yeah, everything, all the signals, including your own, are coded as -1, 1.
Okay.
Okay?
But for the friend signals, it is, if I have 5 friends who have the correct signal, this is coded as 5, right? Not as 1.
Yeah, it's 5. So basically,
So the coefficient is multiplied, not with 1.
yeah, so it's basically in some sense, it's the weight you put on everybody's signal, right? So it's a weight you put on a direct friend signal, on an indirect friend signal. So these are the weights. So you can compare it, because the thing is, like, let's say that what you do is, you just get the signals. Let's say you have your own signal, I hear your signal, okay? And this is all the information I have, right? So in this case, what I would do is I would just, I have two signals, mine and yours, or like, say I have two friends who give me information, right? Both of these signals say answer is A, my signal says B, right? I should just use majority voting. That's the best thing I can do, right? But let's say that, I get your information only, so I'll tell you, we interpret this as decay. But let's say that I get, I have two friends, including you, but I only listen to you with some probability, okay? So when I listen to you, when I listen to both of my friends, then basically it's there. But if I only listen to you with some probability, then let's say with probably only 10%, then you will get something like this, okay?
Because the functional form
Mm-hmm.
of the regression,
Yeah.
you are estimating the coefficients that are multiplied with the aggregate signals from all your friends. So
Right, but I mean, if you don't,
and 7 of them got a correct signal. Then
yeah, you could, instead of looking at this regression, what you could just say is like, say for each friend, I do an independent term, okay?
but you didn't.
No, but it's the same thing. If you do for each friend an independent term, and what you just do is you make the parametric assumption, the coefficients on direct friends are the same, then you get the same equation.
Okay, yeah, I'm not saying it needs to be wrong. I'm just saying that interpreting the size of the coefficients is difficult because the thing you're multiplying it with in the only signal case is one is between -1 and 1. In the other case, it can be between -50 and +50.
Well, I don't quite agree. I mean, most people don't have as many friends. I mean, but even if you have like, even if you have like 3 or 4, I mean, you would get exactly the same thing if you just have like for each friend a single term and you just assume that the coefficients are the same. So if you have for each friend an independent term, it's also between -1 and 1. I mean,
Is the sum normalized or not?
no, if it's normalized, actually I would argue if it's normalized, you would have a problem. Then you couldn't interpret it. But we didn't normalize it. Yeah, we can do it offline. Okay. All right. Now, so I argue that the problem here is more like, this is a social network. And, for example, if you just look at the data, you look at whom people talk to, it's only about 50% of the time that they talk to friends. About 50% of the time they talk to people who are not friends. So there's a lot of like, random communication going on. You run into people, and so this is, you can't get, this is coming from this part of the experiment where we ask about conversations. So when we, I show you in a minute how we did this. But when you ask people about whom they actually talk to, about 50% of the time they talk to people who are not their friends. Okay, not their direct friends at least. So basically, this is we might just basically mismeasure. The right-hand side might have a lot of measurement error in there because social network doesn't equal the conversations that happen. So what we did is, we each time they submitted answers, we asked them to we asked them whom they had talked to. And the way we asked that is we asked them how many people did you talk to. And we asked that question first, and it didn't show any of this panel here, okay? It just showed them how many people did you talk to since last time. And if they said 4 people, as soon as they submitted the answer, we then asked them who they actually were. And we tried to make it really simple by, them doing autocomplete. So basically, they just could start typing in this field, would autocomplete it and suggest who the people were, because we knew everybody who participated in the study, okay? And well, so it's one concern is like, did this actually work? Did we actually get useful information out of this? And so on average, people reported that they talked to 2.3 people. And in the subsequent part where they had to name them, they named 1.7 out of them, okay? Which is 75%. Okay? So we think that's fairly good. Now, another concern is that the people they named might be completely random people. Maybe they just name somebody because they want to get it over with, but not people who actually talk to. Now, what we had is actually when we did the autocomplete, we had a complete roster of all the Harvard students. But out of 4,800 students, well, 3,200. Out of 3,200, because these were 2 years, only about 900 participated in the experiment. Okay? Moreover, people participated at different times. They were invited, but most of them signed up within a 24-hour period, but they signed up at different times. So what we looked at is, if you report somebody, is this sort of a valid link in the sense that this is somebody who participated in the study, who signed up and already looked at the signal, okay? Who signed up before you submitted your answer, okay? And that was true for 83% of the reported links, okay? Which is much, much higher than if they would just randomly report links. So we think that, we got a pretty, we think we got reasonably good data for that. Okay, so these are sort of typical conversation networks. And now we know for each link, we know a timestamp. We know when somebody reported that they talked to somebody else. Okay? It only gives us an upper bound because we don't know exactly at what time they talked to, but we got at least some information. For example, if Peter reported he talked to Sanjeev yesterday, and I report today that I talked to Peter, I know that Sanjeev's information could have traveled to me through Peter. So these are sort of two typical, two examples. And now I'm repeating exactly the same exercise I showed you before, except that I'm doing it now with the conversation networks. Okay? You have a question? Oh, okay. It's exactly the same, just with the conversation networks. And sort of a couple of things here stand out. First of all, the intercept is smaller. So the intercept smaller is basically means that we capture more of the, we capture more information with the right-hand side variables. Okay? Now, the correct signal still has a very high weight, but if you remember maybe before, on all the direct signals, the coefficients were 0.1, and now they're 0.5. They're 5 times as big. Okay, and basically we interpret that as evidence that basically before we counted many people's signals whom you actually didn't talk to. Okay, but now we know who you talked to, and therefore would expect that the coefficients go up. You still overweight your own signal, but you have a much higher weight now on the signal of direct friends. And for indirect friends, the coefficients are smaller, but you see here, if you look at the pattern is actually similar as before. So for the direct friends, you see that the coefficient essentially doesn't change when I have more paths connecting me. Okay, it's about between 0.5 and 0.6. Whereas for the indirect friends, it's almost a linear pattern. Each additional path increases the weight I put on that person's signal. Okay? So we have the same pattern as before, but much larger coefficients. Okay? And some of the confounding effects that we had before, where we didn't quite know, what is a social network and what does it have to do with conversations, are not, are kind of mitigated here because we have the actual conversations. Sorry, yeah.
Is it possible with the data you have to compute what the perfect Bayesian agent
Yes, yes. So I'll, yeah. So this is sort of what we do next. So now, just looking at the patterns on an informal level, that's actually sort of more consistent with sort of a streams model than a degrowth model. And here's a reason. Let's say that information travels between, on a direct link, information travels for sure, but on an indirect link, I only transmit indirect information. For example, Peter transmits his signal to me for sure when I ask him, but he only remembers Sanjeev's signal only with some probability. Okay. In this case, I would expect that basically, for indirect signals, each additional path basically increases the probability that I hear about that I take that signal into account. But for direct links, that effect won't be as strong because Peter already told me his signal. When I ask him, and sort of if I have extra paths, in the degrowth world, I would overweight Peter's signal. But in the streams world, I wouldn't, because I already know that I already know what Peter's signal is. So, there's some notion here like that if you live in a world where there's information decay, it's actually not trivial to like distinguish those two models of degrowth and streams. And here's the reason. Say again here, like you have the sender and receives information from the receiver. Now in the degrowth world, and let's say that indirect information is transmitted only with probability R. Then in the degrowth world, you receive, on average, 2 R signals. And in streams, you receive, in expectation, 2 R minus R squared signals. Because if you receive the same signal, you're not going to double count it. Okay? And if R is large, then these are very different numbers, obviously. It's 2 versus 1 if R is 1. But if R is small, then these two numbers are hard to distinguish, just statistically. Okay? So basically, it's sort of this essentially is the problem of distinguishing these models when you have decay. And typically these when we analyze the growth models, we don't most theory models don't put decay into this framework. Okay? We just assume that we keep averaging over everybody's opinion, but there's no decay. But in this experiment, at least, there seems to be a lot of decay. And when there's information decay, then these models are hard to distinguish. Well, this is what we're trying. Yeah. So,
what the value of R is.
Right. I mean, sort of that's what we're trying to estimate now. Yeah. So, so this is sort of a structural model. Now, I'll assume that direct information passes for sure. So if Peter tells me something, I learn his signal for sure. But indirect information travels only with probability R. Okay? So let's say that this is the model. And so we focus now on everything travels only distance 2. If there's enough decay, then that's okay. And agents get their signals, and then they make a logistic decision with a parameter beta. They make some noisy decisions. They get the net number of signals, and they make some noisy decision. Okay? All right. Now we have two approaches to estimating the model. One is maximum likelihood, where what we do is we actually take the actual conversations, and we calculate the log likelihood and the gradient, the Hessian, and we just use like Newton-Raphson to like sort of fit the model. Okay? That's one approach. The other approach is to actually look at the regression results I've given you before and compare them to the parameters you would expect theoretically, and then they use a sort of method of moments approach to sort of fit the parameters. Okay? So that has the advantage that it's a little bit more intuitive because you see what's going on. So here is, so the theoretical values in the growth and streams model of what you would expect. So the gammas are the coefficient on direct information from direct friends, where L is the number of paths that connect you. And the delta L are the coefficients on indirect information. So these are people who are distance 2 away from you, and L is again the number of paths that connect you. Okay? Right? So you can sort of check, and O is the underweighting you apply to other people's signals versus your own signal. Okay? So this is so you can calculate the formulas for degrowth and streams. And okay, and then basically, what we think is true, something we still have to check. What we think is true is basically the regressions I've shown you before should give you, the coefficient should be equal to those estimates, to the theoretical estimates. Okay, I mean to the theoretical values. It's not totally trivial because in the structural model, basically everybody's signal is going to, the extent to which it matters for my decision is stochastic because it depends on like whom you communicate with. It depends on like the realization of if Peter, for example, tells me Sanjeev's signal or not. all these coefficients are the average effects. Okay? But we think in the regression, essentially, this error term soaks up the fact that there's some noise in the communication. And we just checked it with some Monte Carlo simulations to make sure that this is correct. And the green and the red are sort of the exact values in the streams and the growth model for special parameters. And then we do the simulations and we calculate the regression coefficients to just check that they are close to what we would expect. Okay? And then what we do is we basically try to sort of fit those parameters I've shown you before to the regression coefficients using a method of moments approach. Okay? So one way to do that is to just see, like, you take different R's and different O's, you calculate the coefficients, you compare it to the regression coefficients, you calculate the sum of squares weighed by the variance with which you estimate these regression coefficients, and then you see what minimizes the square of the sum of the variance, okay? This weighted sum of variance. And so this is what we get. So the blue line here are the regression coefficients for direct and indirect friends. And here are the standard errors. And then the green line is what we would expect with the streams model. Okay? And the red line is what you expect with the degrowth model. Okay? And when you estimate it, basically you'll find that the sum of squares is much lower for the streams compared to the degrowth model, which is some evidence. And just to sort of explain, where the identification is coming from, is really coming from the fact that, I show you these coefficients here. It's really coming, the identification comes from the fact that for direct friends, the coefficients don't change. They only change for indirect friends. If for direct friends, the pattern would be that the coefficients are increasing with every path, that would support the degrowth versus streams model. But because we don't find this pattern, we only find it here, that's consistent with the streams model. Okay? Well, decay is always there. Yeah? But yeah. So the reason why the predictions of the models are similar in this case here for indirect friends is just because of this figure I just shown you before, the 2r minus r squared. Okay? Because this is noisy. Because it's noisy, the two models on this domain here for indirect information give you almost the same prediction. So it's hard to identify and distinguish the two models. Whereas for direct friends, if you think that direct information is much more likely to travel directly, it's much easier to distinguish those two models. Okay? So that's the, that's essentially the intuition for why, why we find these different why we find a better fit for the streams versus the degrowth model. Okay? Okay, we do something else, and which is pivotal sources. And this is sort of, I like this actually. This is sort of, so far we haven't exploited yet that we actually have three questions, right? We have three questions. And so what we can do is, so we used, we identified pivotal agents, and we used it the following way. We looked at question 1, and you can do the same thing with question 2 or question 3. We looked at question 1, and we looked at agents who update the information, who choose an action, or who make a choice which is different from their own signal. And if their choice is different from their own signal, it must be because there was somebody in the network who influenced them. Because otherwise, they have this strong bias toward submitting their own choice. So if they don't submit their own choice, it must be because they talked to somebody in the network who changed their mind. Okay? So what we do is we call those pivotal agents. We count everybody in your conversation network, who has a signal different from yours, consistent with your action, and we call those pivotal agents.
And there's no temporal information here?
No. I mean, there's temporal information in the conversation network, the way it's constructed.
Not in this one here.
No. Yeah, and so the idea is basically the pivotal agents are likely agents you listen to with a higher probability. Okay? And then we look at how strongly pivotal and non-pivotal agents influence you in question 2 and question 3. And remember, question 2 and question 3, we draw the signals independently from question 1. So it has nothing to do with question 1, okay? However, the sort of idea here is that if I talked, if Peter talked to Sanjeev and, and somehow let's say I have the following scenario. I say A, my signal says B, Peter's signal says B, but Sanjeev's signal says A. Okay? So my action is consistent with Sanjeev. It may be like somebody else who says A. Maybe I have another direct friend who says A. So basically, Sanjeev would be a pivotal agent. And the idea is that, I'm quite likely to have picked up Sanjeev's information through Peter. And if I'm quite likely to have picked it up through question 1, I'm also more likely to have picked it up through questions 2 and 3. Because Peter somehow remembered that he talked to Sanjeev, and Sanjeev said, okay, it's, this is a pattern of answers. Okay? All right? So if you accept that argument, then you would expect that I somehow weight Sanjeev's signal more heavily for questions 2 and 3 as well. Okay? So this is why I call Sanjeev pivotal. And so what we do is we just run exactly the same regression as before, except that we distinguish between pivotal agents and non-pivotal agents. And I suppressed here direct agents. So there was no space here, so I only report the coefficients for indirect friends who were, indirect conversation friends who were pivotal and indirect conversation friends who were not pivotal. Okay? And because of pivotal agents, I assume there's a higher probability I listen to their signal. Essentially what I'm doing is I'm raising the R. The R was a problem which makes it difficult to distinguish those two models. But if I raise the R somehow, it makes it easier to distinguish it, okay? And this is what you find here. Basically, for the non-pivotal guys, we see exactly the same pattern as before, that each additional path matters. But for the pivotal guys, the coefficients are much higher. So that's consistent with this interpretation that I'm listening to their signals more. But also you see that sort of this monotonicity is gone. Okay? Which is consistent with a streams interpretation versus a Degoda interpretation. Okay? But essentially what we're doing here is, the intuition is exactly the same as before, that we are trying to increase the R. We're trying to focus on agents who have a high R. Because that makes it possible to distinguish those two models. Okay? So I'm almost out of time. Just telling you about the second thing we're doing, this treasure hunt 2. This is together with Arun Chandrasekhar, Emily Breza, and Abhijit Banerjee. And what we're doing there is we're sort of trying to revert this. So there is a lot of there's a sort of interest in trying to sort of identify, if you do a field experiment, say microfinance experiment. You tell people there's this great microfinance program, or there's this great fertilizer also. You want to start this diffusion process at the right point. So you want to infect the right people with this information. People who like multipliers, people who tell others about it. Okay? Or if you want to advertise a great product and you want to give people some free samples, you want to get the people who are likely influencers. Right? So you want to identify the influencers. And identifying the influencers, one way you can do this, you can do a complete network survey. And that's very expensive. Because network surveys are just expensive. Now, a cheaper way of doing it is, we think our treasure hunt might prove to be a cheaper way of doing this by doing something like a treasure hunt, and you see who does best. And the people who do best would actually be the people who are the best connected people. Okay? And so this might be a way of identifying who is doing well, and then you could try to target those guys in a subsequent study. So the design we are implementing right now, and we ran it into pilots, and then we expanded to 20 or 30 villages. It's we do a sign-up. Surveyors go from house to house in a village. They collect the names of people, but they don't do a social network survey. They assign household IDs. And they tell people, they give them a card with a phone number, and they say, if you call that phone number, you get 20 rupees.
Sorry, just to be sure I understand.
Yeah.
So this treasure hunt would say that if I can solve the treasure hunt correctly, I'm the sort of person who gets information from many people.
That's right.
That's not necessarily the person I want to target, but I want someone to spread the information. Because,
Right.
I send you the information, you say, well, thanks very much. And then, nobody talks to you. You only talk to people when you seek information. Is that?
Right. So we're doing, so we're doing some other things. Like, you're right. I mean, it's not, what you would like is like, the central guys, for example. And this does not necessarily identify them.
So I think I'm making a somewhat more sort of narrow point, which is whether the network is really directed or undirected.
Yes.
And
So actually, one of the informations we check is when they call in. I have to finish up, but when they call in, we actually say like, did you go to this person's house, or did the person come to you? So we ask some of these information. But anyway, so we do this like, we have a sign up. People go there. We promise them 20 rupees if they call the number, and this is sort of a warm up round. They do the initial call, and after we do the initial call, we tell them that there's going to be a follow up game, and the follow up game is again the same. You have to call the number. But we're going to send you, you have to find out a 6-digit number. And we're going to tell you one digit out of the 6, and everybody in the village is going to know one of those digits. Okay? And we're going to tell you, we're going to send them an SMS, plus we do a direct call. Tell them this number. And then, it's very similar to a treasure hunt. It's a stochastic ending. So we start on a Thursday, it runs until Sunday or Saturday. We don't exactly tell them when it's going to end. So they have an incentive to call as often as they can. For each number they find out, for each number they say correctly, they get 50 rupees. So they can get 300 rupees at most, okay? If they get all the 6 numbers right. And we have linear incentives, and some digits are harder to find than others. So the first digit is the easiest one. Most households get, many households get that, and the 6th digit is the hardest one. And we want to run more treatments, like vary that more, but we just ran the pilot so far, okay? But what we want to do is after that, we want to run this on 20 villages, and then we want to take 10 of those villages and use the network surveys, because there were previously done network surveys in those villages, do the network surveys and do injection based on the network surveys, and then do injection based on the treasure hunt and see how well we do relatively, okay? And if we can do without using network surveys. Okay, that's it. Thanks.
Okay, thanks very much.